Namaste students, welcome back to Rama Teaches You. Today we are going to do the second video of chemical bonding and molecular structure, the English video. So in the last class, the last topic that we did, the last video was the Lewis representation of simple molecules, the Lewis structure. So we are going to see what the structure looks like. Okay. So the structure that provides a picture of bonding in molecules and ions in terms of shared pairs of electrons and the octet rule is called the Lewis structure. This whole thing becomes the Lewis structure. Although these structures do not explain the bonding and the behavior of the molecules completely, yet they are helpful in understanding the properties and the formation of molecules to a very large extent. Okay, so this is something that we have to learn before we can understand the other complex topics. This is something that they started the whole journey of formation of bonds from this Lewis structure only in the ninth class, chemical bonding and molecular structure. The same chapter, I think atoms and molecules was a chapter. Okay, let's go. Now, although these structures do not explain the bonding and behavior of molecules completely, yet it is a great help. Steps for writing Lewis dot structures. The Lewis dot structure can be written by adopting the following steps. Step number one. Count the total number of electrons required for writing the structure by adding the valence electrons of the combining atoms. All we have to do is to basically draw the two atoms, okay, and draw the valence electrons that they have, and then we have to figure out how to basically fill these valence electrons. Okay, so the outermost orbit should have 8 electrons. That's it. If you can have this fulfillment, then you can draw the valence structure. Write the chemical symbols for the combining atoms and skeletal structure of the compound, and try to distribute the total number of electrons as bonding shared pair between the atoms in the properties of the in proportion to the total bonds. Generally, the least electronegative atom occupies the center position in the atom slash ion. What is electronegativity? Electronegativity is the ability of an electron to ability of an atom to basically attract the shared pair of electrons towards itself. Okay, so generally the least electronegative atom occupies the central position in the molecule, and it is called the central atom. After distributing the shared pair of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as such in the form of lone pair of electrons. So, in I think I have already taught you this. There are two types of electrons when it comes to an atom. Okay. Now, when an atom is forming a bond with another atom, the electrons that are participating in the formation of the bond, the electrons that are participating in the formation of the bond is called the bond pair electrons or the shared pair electrons, and the electrons that are left behind are called the lone pair of electrons. Okay, so they are alone. That is why they are called lone pair of electrons. Okay, now next. So we are going to look at a few structures of various different types of atoms. The first things first, we have the hydrogen atom. Okay, hydrogen atom forming a hydrogen molecule. Now we know that the outermost electron, the number of electrons that is present in a hydrogen atom in the outermost shell is 1. Hydrogen only has 1 electron to begin with. That is a different story. Now basically what is happening, we will draw a hydrogen here. Okay, we will draw a hydrogen here, we will draw a hydrogen here. This is the electron of this hydrogen, this is the electron of this hydrogen, and therefore what is going to happen, this hydrogen atom is going to share these 2 electrons with this hydrogen atom. Therefore we can see that clearly 2 electrons are being shared between these 2 hydrogen atoms, so they will form one single bond between them. Okay, since 2 are being shared, they will form one single bond. Now similarly, you have oxygen molecule. Now we know that the number of electrons that are present in the valence shell of oxygen is 6, so it requires an additional 2 electrons to basically complete its octet. So what does it do? It what does it do? It shares two electrons with the neighboring oxygen atom. Okay, so all in all, there are four electrons being shared between these two oxygen atoms. So if there are four electrons being shared, then there will be two bonds. Similarly, we can do that for ozone. Ozone has a different story altogether. I think in the last video, ozone molecule was the one that I discussed in the last. So ozone molecule, okay, now why does ozone form in the first place? Okay, now oxygen has an atmosphere of six electrons. Okay, now there is one electron here, there is one electron, this is one electron here, and yeah, okay. So these are the all the electrons. No, you are not supposed to draw it like this. Mm, okay, this is one oxygen atom. Now what is happening here? Oxygen is going to share two electrons with the neighboring oxygen to form dioxygen. So what happens here? Look at this. So you have another oxygen atom here. Mm, okay. So these two share these four electrons. They form dioxygen. Now, to form ozone, what do you have to do? One of the oxygen atoms decides to basically share one of its lone pair of electrons by basically transferring both of them to the neighboring oxygen atom. Okay, so it is transferring both of them to the neighboring oxygen atom. Now this atom of oxygen, the one that I'm drawing right now, has around six pair of electrons, eight pair of electrons in its outermost shell. So this is what we call a coordinate bond. Okay, coordinate bond is what? It's not sharing, it's not transfer. It is something like transfer, but it is like a loan. You're transferring it as a loan. They are still your electrons. If an oxygen, if this oxygen decides to leave the ozone molecule, these two electrons will go back to this oxygen atom. Understood? Yeah. So similarly, let's do one for where five atoms are sharing electrons with each other. Now, silicon tetrachloride. This is a very interesting molecule. Okay, silicon is in the middle. Now, can you tell me who is more electronegative? Is it silicon or is it chlorine? Who is more electronegative, Drupad? Silicon or chlorine? Silicon is more electropositive, chlorine is more electronegative. So what did we discuss just before? We discussed that an more electronegative element will share the center stage. So basically here silicon will be the central atom. Okay, now silicon has four electrons, one electron here, one electron here, one electron here, one electron here. Now it is sharing one electron with four chlorine atoms. Chlorine has an atmosphere of 7 electrons. So chlorine is basically sharing one electron with silicon, and silicon is sharing four electrons with four different chlorine atoms. Okay, so that's how the bond is formed. This is a very easy topic initially. This whole chapter is pretty easy. If you think about it, it is nothing but a structure, a structural way of actually viewing our electrons. One second, Drupal. The last chlorine goes here. So, what are the total number of electrons that are being shared? There are 8 electrons being shared, right? All in all, if you look at the whole big picture, there are 8 electrons being shared via these 4 chlorine and 1 silicon atom. So, 8 electrons gives us 4 bonds. So, if you want to form a bond, okay, if you want to form a bond, you need to have 2 electrons to be in the sharing position. Understood? That is the whole story behind this. Now, let's do the first example. These are all the structures. You can actually go through the structures on your own. Okay. Now, if you have any doubts, you can ask me, obviously. Now, let's actually go on to the example. Now, write the Lewis dot structure of carbon monoxide molecule. The valence shell configuration of carbon and oxygen atoms are 2s2 2p2 and 2s2 2p4 respectively. Therefore, the valence electrons available are plus 4 plus 6 is equal to plus 10. Now, that is the maximum electrons that you can have is plus 4 and plus 6. Now, join carbon and oxygen by a single bond, one shared electron pair, and complete the octet on oxygen. The remaining two electrons are lone pair of electrons. Now, what is going to happen? The molecule contains only two atoms. So step 4 is not required, where we can consider carbon as the central atom because it is less electronegative. So this is the MCQ part of this question. Okay. In a molecule, they will ask you, according to the Lewis dot structure, who is the central molecule in the central atom in the molecule. Now, still, the octet of carbon is incomplete. So we have to restore to multiple bonds. In this case, a triple bond between carbon and oxygen, which satisfies the octet rule condition for both atoms. Now, what is happening here? So, 1, 2, 3, 4, 5, 6. Carbon is forming a triple bond with oxygen. When it is forming a triple bond with oxygen, what happens? The carbons, wait, 4, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, the octet is getting complete. Even oxygen also is having the complete octet. So this is how you form the carbon monoxide molecule electron dot structure. Do you have any doubts in this, Drupad? Yeah, okay, fine, let's go. Okay, write the Lewis structure for the nitrate ion. What is nitrate? Huh? Basically, nitric acid releases the nitrate ion. Okay, sorry, nitrite. No, it's not nitrite. Nitrate, it's nitrite. So NO2 minus. This is the structure that we want. Now, draw the Lewis structure in the same manner discussed in the above example, and you will get the following. So we have nitrogen. Nitrogen has how many electrons in the outermost shell? It has 5 electrons in the outermost shell. Okay, now basically what is happening here, nitrogen, here they have shown that nitrogen is having how many electrons? 6 electrons. It is not the case. Nitrogen is not having 6 electrons. Nitrogen minus is having 6 electrons. Understood? The central atom has basically borrowed one of the electrons from a neighboring atom in its ionic bond. So basically when it gets split, so the nitrogen central atom acquires a negative charge. So we will draw how many electrons? We will draw 6 electrons. Ideally, we were supposed to draw only 5 electrons, but because nitrogen has, in this case, has borrowed an extra electron, making this whole molecule into an anion, we will draw 6 electrons. Now, basically, what is going to happen next? Okay, we will use the electron dot structures. Now, what is going to happen? Nitrogen only needs to form how many bonds? It needs to form 3 bonds to make it stable, right? It needs 3 bonds to make it stable. So how does it look like? See, here it can form a double bond with oxygen, thus satisfying the needs of oxygen. This oxygen's needs are satisfied. Okay, now what is going to happen here? This nitrogen is going to form one single bond with this oxygen. Okay, now you may be asking me, but this oxygen's octet is not complete. See, the thing is, this oxygen gave one of its electron. Okay, it gave one of its electron to this nitrogen, and in this form, what is happening? This bond being formed here is because of this nitrogen. I'll actually remove this. Okay, now I'll actually remove this. This 1 second. This is the double bond, and this is the single bond. Okay, so these 2 bonds that are being formed here, they are purely due to oxygen. Okay, I'll explain this. The bond formed here is due to the oxygen. So a coordinate bond is being formed here. Now, because of this, there is a resonance that is happening. This moves here and here. It basically jumps from one location to the other. This is known as resonance. We will learn more about this in the coming classes. Okay. So this is a bit of a complicated structure, but it's not that hard. Okay, so see, Drupat, these two are nitrogen's electrons. This is one of nitrogen's electron. These two are nitrogen's electron. Okay, but what is happening? There are six electrons that are present here. Okay, since there are six electrons present here, there is another chance of forming a double bond also. Okay, one, two, three, four, five. Okay, fine. Yeah, that is fine. Now, limitations of Lewis approach. Although with the help of Lewis approach, structure of several molecules can be explained, but there are certain limitations of this approach, which are as follows. It fails to explain the formation of the chemical bond. So, why did this chemical bond form? Nobody knows. Okay, it also remains unable to explain why bonds are disassociated and bond dissociation enthalpy and bond length in molecules like H2 and F2 are different. See, basically, what the important point in this section is, he's saying hydrogen and hydrogen form what? A single bond. Fluorine and fluorine also form a single bond, but the length of the hydrogen bond is how much? See, the bond length in the molecule of H2 is 74 74 picometer, and F2 is 155 picometer. Why is this happening? He was not able to explain it. Okay. Also, the bond dissociation enthalpy. What is bond dissociation enthalpy? It is the amount of energy required to break a bond. Okay, it is the amount of energy required to break a bond. Why were these bond dissociation enthalpies so different, even though both the molecules have a single unique bond? Okay, then why are they so different? Why is their length different? Why is the amount of energy to break these bonds different? He was not able to explain. The Lewis dot structure fails to explain these theories, although both of them involve the formation of a single covalent bond by sharing an electron pair between the respective atoms. Okay, it also does not give any idea about the shape of the atomic molecule, polyatomic molecule. What shape will it have? Okay, this basically looks like a two-dimensional picture. Okay, we want to know. See, atoms and molecules are not two-dimensional; they are three-dimensional structures. Okay, so when they form a bond, they will also have a three-dimensional structure. So they were not. He was not able to explain the three-dimensional structure of the atom. Okay, now the next topic that we're going to discuss is formal charge. Generally, Lewis dot structure do not represent the actual shapes of molecules. For example, polyatomic ions, the net charge is present on the ion as a whole instead of a particular atom. For example, this HNO2 minus. When we saw this HNO2 minus, what is this? This is a formal charge. The minus is not on just nitrogen. It is on the whole molecule. It is on the molecule as a whole. Okay. Now, for polyatomic ions, the net charge is present on the ion as a whole instead of the particular atom. However, it is more feasible to assign a formal charge on each atom. Okay, what does that mean? For example, Drupad, let us look at sodium chloride. Okay, I know it's an ionic bond, but just humor me. Sodium chloride, when we draw the structure of sodium chloride, what is happening? Sodium is losing one electron to chlorine to form an ionic bond, right? It is forming an ionic bond via the transfer of one electron from sodium to chlorine. Now, because of this dan, because of this loan, what is happening here? Sodium is getting a positive charge, plus one charge, and chlorine is getting a minus one charge. Similarly, we are going to assign certain charges on each and every single atom in a molecule, a certain amount of charge. The formal charge of an atom of a polyatomic molecule or ion may be defined as the difference between as the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to the atom in the Lewis structure. So this whole thing is how we are going to calculate the formal charge. Now, formal charge can be calculated as number of valence electrons minus the total number of lone pair electrons, and what is S? The total number of shared pair of electrons. Now, formal charge is equal to valence electrons minus lone pair of electrons minus 1 upon S shared pair of electrons. Okay. Now, in it is a factor which is based on pure covalent view of bonding. Okay, here formal charge is a concept that we use when we see the bond as a purely covalent bond in which the electrons pairs are shared equally by the neighboring atoms. Formal charge do not indicate the real charge separation within the molecule, but it only helps in knowing that keeping track of the valence electrons in the molecule. Moreover, it also helps to select the lowest energy structure from a number of possible Lewis structures for a given species. Generally, the Lewis structures having the smallest formal charge on an atom is of the lowest energy. Now, how are we supposed to calculate the formal charge? Now, the sum of the formal charge in the molecule. So, Drupad, the say in the case in this it is the case same as that of an ionic bond. In an ionic bond, the sodium has a +1 charge, chlorine has a -1 charge. But when you add both these charges, what do you get? +1 -1 is equal to 0. You get an overall charge to be 0. So when several Lewis structures are possible, the one with the formal charge closest to 0 is most stable and is preferred. This will be an MCQ question or a one marker. Calculate the formal charge on each oxygen atom in an ozone molecule. So first things first, we will write down the formula. Formal charge is equal to, what is the formula? Number of valence electrons minus lone pair of electrons minus half the number of shared pair of electrons. Now, the Lewis structure of oxygen O3 may be defined as the oxygen atom have been numbered as 1, 2 and 3. So, oxygen number 1, oxygen number 3 and oxygen number 2. The central oxygen atom is marked as 1. So, how many, what will be the formal charge on the central atom? The formal charge. So, Drupad, I'm asking you this one question. Tell me how many electrons are present in the valence shell of this oxygen atom? How many electrons are present in the valence shell of this oxygen atom? Drupad? Yeah. How many electrons are present in the valence shell of this oxygen atom, Drupad? In an oxygen atom, the number of valence electrons will always be 6, right? Minus. How many lone pair of electrons are there in this oxygen atom? How many lone pair electrons are there? Lone electrons are 2 exactly. And how many shared electron? How many electrons are being shared here? See, 6 exactly. So 1 by 2 into 6. So minus of 1 by 2 into 6. So basically there is one electron here, 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 and one electron here. So all in all, 6 electrons are being shared. So what is the formal charge that we'll get? So this will become 3. So 6 minus 2 minus 3 is equal to +1. So the central oxygen atom has a formal charge of +1. Next, for this oxygen atom, oxygen number 2, again the number of valence electrons will be how much? 6. Okay, there are 6 valence electrons minus how many lone electrons are there? 4. Minus 4 minus 1 by 2 into how many shared electrons are there? 1, 2, 3, 4. 4. So you will get 6 minus 4 minus 2 is equal to 0, right? Okay, so are we getting 0? Yes, we are getting 0 for oxygen second. Now, for the third one, what is going to happen? So, for the third one, this one, how many electrons are there? There are 6 electrons. Now, how many valence electrons are there? One, 2, 3, 4, 5, 6. There are 6 valence electrons. How many shared electrons are there? 1 by 2 into, there are only 2 electrons that are being shared by this oxygen atom. So basically there are 2 electrons. So if you cut this, you will get 1. So 6 minus 6 minus 1 is equal to minus 1. This becomes the overall answer for our question. Hence, the oxygen O3 molecule along with the formal charge can be represented as follows. Now, Drupad, one oxygen atom has a formal charge of plus 1. Another oxygen atom has a formal charge of minus 1. And the third oxygen atom has a formal charge of 0. So what does that indicate? It indicates that basically the overall formal charge in a molecule will be plus 1 plus minus 1 plus 0 is equal to 0. So the overall formal charge in a molecule is always 0. So did you understand the formula? So what is the formula saying? Formal charge is equal to valence electrons minus shared pair of electrons, sorry, valence electrons minus lone pair of electrons minus 1 by 2 shared pair of electrons. Understood? Okay, let's move on to the characteristics of a covalent bond. So characteristics of a covalent bond is a 2 marker. You only need to memorize like 4 points, half a point for each property. Now the characteristics of covalent bonds. Compounds having covalent bonds are called covalent compounds. The physical state. So we know that covalent bond is not as strong as that of ionic bond. So it be because of this weaker strength. And covalent bond can exist in multiple states. It can exist in a solid state, a liquid state, or a gaseous state. Solid state examples are that of carbon. Okay, carbon in the form of diamonds and graphite can exist in the solid state. Similarly, in the for a liquid state, you have the bromine liquid, right? Bromine is a liquid. H2O is a liquid. It's a covalent bond. H2O is a liquid. And similarly, for gases, we have hydrogen gas, we have chlorine gas, we have oxygen gas. All of these are gases. Okay. Now, low melting and boiling point, because the covalent bond is not as strong as an ionic bond. It does not require that much energy to actually break the bonds. Okay, so the I'm talking about basic. I'm not talking about the bond in per se. I'm just saying the melting and boiling point. The compounds have low melting and boiling points because of the presence of weak forces of attraction between the molecules, which are easy to overcome at low temperature. See, you need to have some kind of bond between two molecules. Now, I'm not talking about atoms in the same molecule. I'm talking about two molecules. Okay. Now, what does it mean? It could be a van der Waals force. It could be a hydrogen bond. It could be a London dispersion force. Okay. All of these are what allow the molecules to stick together. They allow the molecules to stick together, and because of this we have different states. If they have the ability to stick together better, then they will have stronger intermolecular bonds, right? Intermolecular bonds. Now, what happens with the intermolecular bond? If you have a stronger intermolecular bond, then you require more energy to basically weaken this bond, or to simply break this bond. You will require more energy, and this more energy you usually get from the basically by heating or by providing electricity, by increasing the temperature. So that is the reason why they have very low melting and boiling points, because their intermolecular forces are not that strong. Okay, next comes solubility. Now, covalent bond are usually nonpolar. Being a nonpolar means what? For example, in the case of an ionic bond, there are two poles at the end of that bond. There is a positive in the cation and the negative in the anion. So it's a polar molecule. Whereas, because of the sharing, most of the covalent molecules are non-polar. There are a lot of exceptions to that too. We are going to learn more about that in the coming classes. Okay, so being non-polar, these are general being non-polar, these are generally insoluble or less soluble in water and other polar solvents. However, these are soluble in non-polar solvents like benzene, ether, carbon tetrachloride, etc. Now, covalent bonds having hydrogen bonding can be dissolved in water. Okay, the best example is that of alcohols. Now, in class 10th, you have learned about alcohol groups, right? In the carbon and its compounds section. So, what is an alcohol group? You have the R, O, H, where R could be any kind of alkane, alkene, or alkyne. For example, CH3, CH2, OH. What is CH3, CH2, OH? Drupat, what is the name of this molecule? CH3, CH2, OH, ethanol. Now, in this ethanol molecule, the oxygen is an electronegative element, whereas hydrogen is an electropositive element. So, what happens inside this oxygen bond? The oxygen, we have already discussed what an electronegativity is, right? It is the ability of an atom in a molecule or in a bond to attract the electrons towards itself. So the electrons that are being shared between oxygen and hydrogen are attracted towards oxygen. Therefore, what happens? The oxygen has a negative charge, whereas hydrogen has a positive charge. Oxygen has a negative charge, hydrogen has a positive charge. Now, there is a what is happening due to this? A polarity is being shown here. In a covalent molecule, a polarity is being shown. So this positively charged hydrogen will now try to attract the negatively charged atom, oxygen, in water. So oxygen in water also exists like this only. Look at this. This is oxygen, this is hydrogen, this is hydrogen. Oxygen, being selfish, is basically attracting both the electrons towards itself. Therefore, it is having a positive charge here, a positive charge here, and a negative charge here. So, the positive of one hydrogen atom in a molecule is attracting the oxygen of another atom, oxygen, in the water molecule. So, this is what we call a hydrogen bond. Because this bond involves the hydrogen atom, we call this bond the hydrogen bond. Drupat, am I making myself clear or should I repeat myself? Okay, so we know that ethanol is what? It's an organic molecule. Carbon is forming covalent bonds with all the hydrogen atoms. Now, the polarity in the carbon hydrogen bond is being cancelled out. Okay, so the only polarity that remains is that of oxygen and hydrogen. Now, this oxygen and hydrogen are forming a single covalent bond, right? They're forming a single covalent bond. So, ideally speaking, the electrons should be shared like this, right? The electrons should be shared in the middle, but that's not what happens. Both the electrons that are being shared lie closer to the oxygen atom. Okay, due to which what happens? There are more number of electrons in the electron cloud of oxygen. Therefore, oxygen now attains a partial negative charge. Not a completely negative charge, -1, but a partial negative charge, delta minus. This partial negative charge is because of the attraction or the addition of a slight a fraction of an electron towards itself. Now similarly, because oxygen has a partial negative charge, hydrogen has a partial positive charge. Now this hydrogen atom with its partial positive charge is now able to attract this oxygen having a partial negative charge. Okay, this oxygen in the water molecule is having a partial negative charge due to the same reason, oxygen being more electronegative than that of hydrogen. So basically, this oxygen atom, these two are the shared electrons that are being shared between oxygen and hydrogen, but because of oxygen's selfishness, it is attracting both these electrons towards itself. Therefore, this is having a partial negative charge, and the water molecules hydrogen are having a partial positive charge. Therefore, now this is the hydroxyl bond. This is a water molecule. So this hydrogen ion is now getting attracted by this oxygen ion because of this hydrogen's positivity and this oxygen's negativity. So what the instead of forming an actual bond like a covalent bond or an ionic bond or a coordinate bond, they are forming a hydrogen bond. Okay, so this is known as a polar bond. Understood? So this is known as intermolecular bonds, a hydrogen bond. This is part of hydrogen bond is part of the intermolecular bond group. So this belongs to the intermolecular bond groups. A few other bonds that belong to this group are the Van der Waals bond and the London dispersion bond. More about this in the later classes. Understood? So any doubts? Were you able to clear your doubts here? So that is the reason. Because of this formation of a hydrogen bond, covalent molecules that can form covalent molecules that can form a hydrogen bond can be dissolved in water. Understood, Drupak? Is this explanation clear, or should I explain it once more? Thank you so much. Let's move on. Now, electrical conductivity. Since there are no free ions in the covalent compound to conduct electricity, they are bad conductors of electricity. However, graphite is an exception. So, why is graphite an exception, Drupat? In class 10th, I have taught you this. Why is graphite the only compound, is one of the compounds, even though it forms a covalent bond, it is able to conduct electricity? Why? Exactly. Carbon, unlike in the case of diamonds, does not form a bond with four other carbon atoms. In graphite, it only forms bonds with three other carbon atoms. So every single carbon atom has one free electron that is just roaming in the layer, roaming in the matrix, roaming in the graphite compound. Right. So due to which what happens when you pass an electric field, when you apply an electric field across this graphite rod, the electrons start moving, the electrons start to conduct, and moving electrons result in current. Okay, that is one of the reasons. Let's move on to the next one. Directional characteristics and isomerism. Since the covalent bond is localized in between the nuclei of atoms, it is a directional in nature. Okay, it is directional. Now, let's move on. Directionality, you know what it means? Basically, the polar molecules, okay, the direction is always from the, I think, positive to negative or negative to positive. I think it's from positive to negative. Okay, like basically, HCl. Okay, HCl. Hydrogen is less electronegative, it is more electropositive. Chlorine is more electronegative. Therefore, what happens? There is a negative positive charge here and a negative charge here due to chlorine's electronegativity. Now, because of this, what happens? There is a directionality. I think this is it. Okay, the directionality in chemistry. I always get confused between physics and chemistry. The directionality always goes from the positive to the negative. Just hold on. Let me just recheck it. I'm going to write the definition of directionality. Okay. So covalent bonds are Covalent bonds are directional bonds because they form through sharing of electrons. Sharing of electrons which requires the overlap of atomic orbitals. Okay, this overlap occurs most effectively if the orbitals align in a particular direction. In a particular direction to maximize the electron density between the nuclei. Between the nuclei. Okay, so that is the reason for the directionality. Okay, we will learn more about this in your, I think, valence band theory or valence electron pair repulsion theory. We'll learn more about this later. Okay, now there are, I think this is the last topic, right? Yeah. There are multiple types of covalent bonds. Okay. Types of covalent bonds. Depending upon the electronegativity character of the combining atoms, the covalent bonds can be of two types. Non-polar covalent molecules. When the covalent bond is formed between two atoms, when a covalent bond is formed between two atoms having almost the same electronegativity, then the shared pair of electrons are equally shared by the two atoms and situated exactly between the two identical nuclei, or in other words, they form a homonuclear atom. This type of covalent bond is called a non-polar covalent bond. This type of bond is usually found between two similar atoms. Now, I have told you what is the reason for the polarity in a covalent bond. It is due to the difference in the electronegativities of the atoms that are participating with each other. Okay, it is due to the difference of the electronegativities of the atoms that are participating with each other. Now, think about this. If two atoms are equally selfish, they are equally electronegative, then what will happen? If both of them are equally electronegative, equally selfish, they would not allow the other to simply pull the shared pair of electrons towards themselves. They will always fight to keep the shared pair of electrons between them, exactly between them, so that basically one does not get affected by the other. Okay, that is what a non-polar molecule looks like. For example, in the case of hydrogen, both of them have the same electronegativities. Let us take the example of oxygen, chlorine, fluorine, bromine, and nitrogen. All of these are examples of molecules where the electrons are shared exactly in the middle. Neither of them is ever going to gain a partial positive or a partial negative charge. Understood, Drupad? Did you understand this logic? Okay. Now, polar covalent bonds. Okay, this is the next topic. When a covalent bond is formed between two atoms having a significant difference in their electronegativities. For example, let us take the example of hydrogen and fluorine. Okay, an electropositive element and one of the most electronegative elements in the whole periodic table. Then the shared pair of electrons slightly shift towards the more electronegative atom, and the bond thus formed attains a partial ionic character. This type of covalent bond is a polar covalent bond. Understood? This is what we call a polar covalent bond. This type of bond is usually formed between two dissimilar or heteronuclear atoms. Example, your hydrogen chloride, hydrogen fluoride, water molecule. Okay, all of these has a center of positivity and a center of negativity inside the molecule. For example, let me give you the example of hydrogen and chlorine. Both the electrons are much closer to the oxygen atom. So we have a center of positivity and a center of negativity in a molecule that has agreed to share the electrons with itself, right? With each other, they have agreed to share the electrons. But still, what is happening? But still, you find a center of positivity and negativity. Did you understand this, Drupad? Polar covalent bonds. Okay, now limitations of the octet rule. What are the limitations of the octet rule which led us to find different other types of theories? Although the octet rule explain the formation of a large number of covalent bonds, but it has a few exceptions also, which are discussed below. Number one, the electron deficient molecules. Incomplete octet of the central atom. So the octet rule says what? If an atom is able to attain the magical electronic configuration 8 in its outermost shell, then it will magically become stable, right? So if any molecule is unable to do so, then it will never be stable. But that is not the case in nature. We see there is a lot of atoms, we see that there are a lot of atoms who have what? Once again, Drupad, just once again. So incomplete octet of the central atom. There are some molecules in which the central atom is surrounded by less than 8 electrons. Their octet is incomplete. Elements having less than 4 valence electrons generally form molecules of this category. For example, you have your BeCl2, barium chloride. Okay, beryllium, beryllium chloride. So basically, beryllium is surrounded by only 4 electrons, whereas both the chlorines are happy. They are surrounded by 8 electrons, but the central atom beryllium is only surrounded by 4 electrons, and that is not correct, right? So BF3, BF3, what is happening? Boron, the central atom, is only surrounded by 6 electrons. Similarly, BeH2, again 4 electrons. Now, do these chemical bonds do not form? Are there molecules does not exist? No, it is just simply that they are not following the octet rule. That's it. Now, odd electron molecule. Okay, Drupad, this is a very important topic. Please listen very carefully. It requires couple of readings to actually understand this odd electron theory. Okay, odd electron molecules. Molecules like NO, NO2 and O2 are examples of such molecules in which the bonded atoms, in which the bonded atoms, one second, in which uh, such molecules in which the bonded atoms have odd number of electrons, usually 3 in between them. That's why they are called odd electron molecules. Okay, so again I'm repeating myself. NO, NO2 and O2 etc. are examples of such molecules in which the bonded atoms have odd number of electrons, usually 3 in between them. That's why they are called odd electron molecules. In case of these molecules, the octet rule is not satisfied for all the atoms. Okay, now look at this. For example, nitric oxide, NO. What is happening here? So, species with one unpaired electron are called free radicals. Okay, let's look at this. So, how many electrons does nitrogen have, Drupad? After forming the bond, it formed a bond with oxygen. So, basically, there is one electron here. Sorry, mm, there is one electron of nitrogen here, one electron of nitrogen here, one electron of hydrogen, one here, one here. Okay, so it is having three extra electrons after formation of the bond. It has, this is the odd electron. Oh, sorry. Your nitrogen is having three electrons here. Similarly, let's look at the case of NO2. How many electrons are present in nitrogen now? Again, right? This is what NO2 looks like, right? So again, you have odd electrons. Next, oxygen molecule, O2. So you have how many electrons here? Wait. How is oxygen molecule an odd electron? I'll explain this in the next class. I thought, I think it should be ozone, not oxygen. Ozone. Ozone has odd number of electrons, but oxygen does not, I guess. Anyways, I'll explain. I'll see. I think it's a mistake here. Now, next, these are paramagnetic, and most of them are generally unstable. You know what paramagnetism is, Drupat? Paramagnetism means having free electrons. Okay, unpaired electrons. If you have unpaired electrons, that means you are paramagnetic. Okay, you show magnetic behavior when you're kept in the presence of a magnetic field. We'll learn more about this in the later classes. Now, electron-rich molecules. The expanded octet. Elements of the third and higher periodic tables can expand their covalency due to the availability of the d orbital and can accommodate more than 8 electrons in their valence shell around the central atom. This is called the expanded octet rule. Here also the octet rule is not applicable. For example, PF5 has 10 electrons around the phosphorus atom. Similarly, SF6 has 12 electrons around the sulfur atom. H2SO4 again has 12 electrons around the sulfur atom. So they are also stable molecules, but they are also not following the octet rule. So the octet rule is basically a hindrance. Okay, it is not showing you the full picture of what the molecule should look like. Okay, did you understand this? See, PF5, how many molecules is it sharing? It is sharing 10 electrons. 1. So basically, phosphorus is having 1, 2, 3, 4, 5, 6, 7, 8, and 9 and 10. So basically, phosphorus is having 10 electrons in its valence shell. Okay, sulfur is having 1, 2. Just like this, it is going to have 12 electrons in this valence shell. Did you understand the logic, what I'm trying to say? Okay, compounds having expanded octet are termed as hypervalent compounds. Please remember this term, the hypervalency. Okay, hypervalency means having the ability to have more than 8 electrons in your valence shell. That is known as hypervalent. Another drawback, some other drawbacks of this theory are as follows. Octet rule is based on the inertness of noble gases, but some noble gases like xenon and krypton form several compounds with oxygen and fluorine like XeF2, XeF4, XeF6, XeOF4, XeO2F2, and KrF2. Now, this is something strange altogether. Why? Because what was the octet rule saying with the utmost confidence? If you have 8 electrons in your outermost shell, then you're good. You should be good, right? You should not be able to react. You should not have the need to react with anybody, or nor should you be able to react with anybody. That is what inertness means, right? But here, this xenon and krypton, even though they have this complete configuration, they are able to form bonds. And this is a violation of the octet rule. Understood? Next, it does not tell us about the shape of the molecule and their relative stabilities. Okay, molecules have a three-dimensional shape. What Lewis gave us was a two-dimensional structure of arranging the electrons around the central atom. That's it. Okay, he did not give us a three-dimensional shape. And also, just by looking at the shape of this two-dimensional structure, you cannot guess whether this structure is going to be stable or not. Understood? You cannot guess whether the structure is going to be stable. It fails to explain the paramagnetic behavior of oxygen, which should be diamagnetic according to this rule, but it is in fact paramagnetic in nature. Oh, now I get it. See, Drupad, this does not have odd number of molecules. This is just an example of a normal one. Okay, this does not have odd number of molecules. Okay, yeah, understood, right? Nitrogen, this molecule, this nitrogen atom has odd number of molecules. This also has odd number, and both of these are what? Paramagnetic. Even though oxygen has even number, they shouldn't have written it like this. Even, but still it is. Okay, we will learn more about this when we study the molecular orbital theory. When two atoms come together and basically share their molecular orbitals. Okay, this is known as MOT. We will. I think that's going to be the last topic of this chapter. Next, ionic or the electro. Okay, octet rule is totally silent about last point. Octet theory is totally silent about the energy of the molecules. How much energy will you have? It is to it. We cannot figure out how this forms. Okay, next, the ionic or the electrovalent bond. The bond formed as a result of the electrostatic force of attraction between the two oppositely charged ions, that is the positive and the negatively charged ions together in terms of is known as the electrovalent or the ionic bond. It is formed by the complete transfer of electrons from one atom to the other so that all the combining atoms complete their octet or the duplet in the case of hydrogen, helium, and lithium. So, what is happening here? A transfer is taking place so that both the cation, the positively charged ion, and the anion, the negatively charged ion, both of them are able to fulfill their outermost electronic stable configuration. Okay, let's go ahead. Next, we are going to start with, in general, it is generally formed between a non-metal and a metal atom so that they get converted into an anion or a cation respectively. The number of unit charge present on the ion in the electrovalent is known as the electrovalence of that ion. For example, sodium is able to lose an electron and it is able to form a plus one charge because of the loss of electron. Similarly, chlorine is able to get a negative one charge due to the acceptance of the electron. Okay, so this is sodium and this is chlorine. There is a transfer of electron that is taking place between them. Therefore, sodium is getting a positive charge, chlorine is getting a negative charge, and you can see the structure. You can see the electronic configuration also. When you see the electronic configuration, what do you see? You see this is somewhat the electronic configuration of neon, and this is the electronic configuration of argon. Both of them are noble gases. The number of opposite charges present as the nearest neighbors around that ion is known in a ionic crystal is called its coordination number of that ion. Formation of ionic bond depends on the following factors. Now, what is the coordination number, Drupad? Okay, let us look at what the coordination number is. Again, the number of oppositely charged ions present as the nearest neighbor around that ion in an ionic crystal is called the coordination number. For example, in sodium chloride, okay, in sodium chloride, how many opposite charge, how many the number of oppositely charged ions present as the nearest neighbor around the ion in an ionic crystal? Okay, just hold on one second. So In sodium chloride, in the sodium chloride molecule, how many chlorine atoms are surrounding the sodium atom, Drupad? Sodium ion. How many chlorine ions will be surrounding the sodium ion? Drupad, I'm asking you a question. How many chlorine ions will be surrounding one sodium ion? Huh? See, there will be one sodium here. There will be a Cl minus, Cl minus, Cl minus, Cl minus, one on top of sodium like this, basically like this, and one at the bottom of sodium. Okay, so basically, if I make a structure like this, it will look somewhat like this. This is sodium. This will be chlorine in one side, chlorine this side, chlorine this side, chlorine this side, one on top, chlorine, and one at the bottom, chlorine. Okay, so there will be six chlorine atoms surrounding the positively charged sodium, okay, at all times in the sodium chloride crystalline structure. Then the coordination number of chlorine will be what? Sorry, the coordination number of sodium will be what? The coordination number of sodium will be 6 in NaCl. That's how you picture a coordination number. Understood, Drupad? In an ionic solid crystal, the number of oppositely charged ions surrounding a particular ion will be called the coordination number of that ion. So in the case of sodium chloride, the sodium will have a coordination number of 6. Next, formation of ionic bond depends upon the following factors. The low ionization energy. What is ionization energy of a metal, Drupad? What is ionization energy? Can you please tell me? Drupad, what is ionization energy? What is ionization energy, Drupad? It is the energy that is required to remove an electron, right? It is the, okay. It is the amount of energy that is required to remove an electron in the gaseous state. Okay. Okay. Next, low ionization energy of a metal atom. Ionization energy is the amount of energy required to remove the most loosely bound electron from the isolated gaseous atom to form a positive ion. So, lesser the ionization energy of a metal atom, greater is the ease of losing the valence electron, and hence greater is the tendency to form an ionic bond. Okay, high negative value of electron gain enthalpy of a non-metal atom. You should also have high electron gain enthalpy, low ionization enthalpy. The electron gain enthalpy is the energy change when an electron is added to an acylated gaseous atom to form a negative ion. So, higher the value of negative electron gain enthalpy, greater will be the ease of formation of the anion, and hence greater is the tendency to form the ionic compound. Greater will be the tendency to form the ionic compound. Understood? Okay. Next. So basically, you need to have low ionization enthalpy, high electron gain enthalpy. Okay. So the metal needs to have low ionization enthalpy. The non-metal needs to have high electron gain enthalpy. Now, a qualitative measure of the stability of an ionic compound is provided by its enthalpy of lattice formation and not simply by achieving octet of electrons around the ionic species. In gaseous state, higher the value of the lattice energy, higher is the ease of formation of the ionic compound. You know what lattice energy is? So basically, if you the we know that the in we know that in ionic compounds, they usually are present in a solid ionic crystal, right? They are usually present in an ionic solid crystal. Now, that the arrangement of these ions in the ionic compound or in the ionic crystal is called its lattice. Now, how much energy is required to break this lattice, to break all these ions into these all these ionic compounds into their individual ions, is called the lattice enthalpy. Now listen to me very carefully. If you require a large enough energy to break that lattice, if you require large enough energy to break that lattice, then your ionic compound will be more stable, right? A more stable building, a more stable bridge requires more energy, more efforts to break it, right? But a less stable bridge or a building which does not follow the codes, it will be easier to break that building. Similarly, if the lattice, if you require less energy to break the lattice, it means that you were not stable to begin with. Am I right? Can you make the connection in your head now? Okay, let's move on. Lattice enthalpy, the amount of energy required to completely separate 1 mole of the solid ionic compounds into gaseous constituent ions, is called the lattice enthalpy. This is exactly what I said just now. Okay, the amount of energy required to completely the amount of energy required to completely break the lattice of 1 mole of the solid ionic compound into gaseous constituents is called the lattice enthalpy, or the ionic solid. Now, the value of lattice enthalpy depends on the following characters. Okay, factors. Charge on the ion. Higher the charge on the ion, greater is the force of attraction, and hence larger is the amount of energy released. Example: the lattice enthalpy of some ionic compounds are in the order like this. Look at this. Where is it? Oh yeah, here. For example, sodium chloride. Okay, sodium chloride has what the ionic enthalpy is minus 758. You know what that means? This much amount of energy was released. Okay, when the bond actually formed. This much amount of energy was released when the bond actually formed, and this much amount of energy was released when the bond actually formed. What do you observe here? The more charges are present in the individual ions, the more difficult it is to break them into their individual constituents from their ionic lattice. Okay, did you understand this? So, for example, in sodium chloride, both sodium and chlorine only have +1 -1 charge. In calcium chloride, calcium has +2, but chlorine only has -1 charge. Okay, so but in the case of magnesium oxide, both of them have a plus and a minus symbol. Clear? Huh? +2 and -2. So basically, they are bivalent, and because of their bivalency, their energy release is very large compared to that of sodium chloride. Next, the size of the ions. Larger is the size of the ions, greater is the internuclear distance, and lesser will be the force of attraction. So, to say it simply, if your bond length is very large, the force of attraction, the electrostatic force of attraction that exists between the two compounds will be very small, because the electrostatic force is inversely proportional to the square of the distance. So if you increase the distance, what happens? Then the force of attraction reduces. Okay, now if the force of attraction reduces, less lattice enthalpy will be available. For example, in the case of sodium chloride and sodium bromide, sodium chloride has 758 joules, my amount of energy getting released, whereas in the case of sodium bromide, it is minus 752. The energy released decreased. Why? Because in the case of chlorine and bromine, the bromine is a higher molecule, it's a larger molecule compared to that of chlorine. Similarly, lithium fluoride and lithium iodide. Lithium and fluorine are so small, right? They're very small compared to that of lithium iodide, because iodine is very, very huge. I see fluorine only has two shells, right? Iodine has five shells. Fluorine, chlorine, bromine, iodine. It has five shells around the nucleus. So it will be a huge molecule. Due to which what will happen? Lithium fluoride will be able to generate more more energy when when the bond is being formed compared to that of lithium iodide. So in these cases, you know what type of questions they will ask? They'll ask you this question. They'll ask you, explain to us why the lattice enthalpy of lithium chloride is more than that, sorry, is less than that of lithium fluoride. Okay, they could ask you a question like this. You can say it is because the atoms, the ions are huge. Because the ions are huge, the internuclear inter atomic distances between the two also increases, due to which the force of attraction gets reduced to a large extent. Understood, Drupad? Okay. Now, lattice enthalpy is calculated with the help of Born-Haber cycle, which will be discussed in chapter number 5. If the lattice enthalpy plus electron gain and so if lattice enthalpy plus the electron gain enthalpy is greater than the ionization enthalpy, then the net effect will be the release of energy and hence result in the formation of an ionic bond. Understood? So lattice enthalpy plus electron gain enthalpy should be greater than the ionization enthalpy. You know what that means? Now, lattice enthalpy is the amount of energy required to form the bond. Electron gain enthalpy is the amount of energy released. Okay. Now, when these two energies get released, sorry, lattice enthalpy is the amount of energy released when the bond is being formed. Now, electron gain enthalpy is the amount of energy released when an atom actually takes in an electron. Now, they should be greater than the ionization enthalpy of the cation of the metal atom. Otherwise, what will happen? If they are lesser than the ionization enthalpy, then the electron will never be able to come out of the metal atom, right? The electron will never be able to come out of the metal atom to form the metal ion. Am I right? Drupad, am I right? Yeah. So see, that is the thing. See, basically, you need to generate enough energy, more than enough energy, to actually start the process. Okay. So basically, the energy that is being released is being used by sodium to actually remove the electron. See, ionization enthalpy is always going to be positive. Why is it positive? Because the electron present inside the atom is always negative. It has negative energy. Now, if you want to remove the electron, you need to provide the atom with energy, right? So that is why I'm saying to remove the electron, you need some energy. That energy should be provided by the lattice enthalpy and the electron gain enthalpy, which will continue the cycle of formation. I think you don't understand this, right? Like, is it actually clear, Thrupat? Yeah, I'll give you a better example. See, the salary that you get from your job should be higher than your expenditure, like your rent plus your utilities plus all the food that you buy from outside and all the entertainment that you have. All of their expenditure should be less than your actual salary, right? If it is more, what will happen? You will have to borrow. You will have to live on credit cards. Am I right? Similarly, what they're trying to say is the energy that is being released. Where, in which two situations are we getting the energy release? We are getting the energy release when the metal and the non-metal is forming a bond to form a lattice. That is one energy release. The second is when you provide an electron to a non-metal, it releases energy in the form of electron gain enthalpy. So the source of your energy should always be higher than the consumption of an energy, which is the ionization enthalpy. Clear? This is an MCQ, Drupad. This is a very well hidden MCQ. Okay, this you can mark this in your book. A lot of times they will ask you, they'll give you the ionization enthalpy, the electron gain enthalpy, and the lattice enthalpy, and then they will ask you, will this situation, will this situation lead to the formation of an ionic bond? So you have to say with confidence no or yes, it will form an ionic bond. And you'll have to show it like this. The lattice enthalpy plus the lattice enthalpy plus the electron gain enthalpy should always be greater than the ionization enthalpy. Am I correct? Are you able to understand what I'm trying to say? Are you buying what I'm selling? Okay, let's move on. Now, properties of ionic compounds. The compounds in which ionic bonds are present are called ionic compounds. Just as in the case of covalent compounds and covalent bonds, we discussed about their properties, right? Like their melting point, their solubility, their boiling point, okay, their state. Similarly, we are going to do that for the ionic compounds also. Now, the physical state, usually ionic compounds are present in the solid crystalline state. The compounds generally exist as crystalline solids known as crystal lattice, which consist of orderly three-dimensional arrangement of cations and anions held together by a Coulombic interactive energy. So basically, like for example, a sodium atom like this will be surrounded by one chlorine here, one chlorine here, one chlorine here, one chlorine here, and one chlorine at the top and one chlorine at the bottom. Okay, so similarly, this chlorine will be surrounded by a sodium here, a chlorine here, and then a chlorine here. So basically, it is we are going to form a three-dimensional matrix. Okay, a three-dimensional crystalline solid matrix is that what we get. Now, similarly, the melting and the boiling point. In ionic compounds, the ions are tightly held together by strong electrostatic forces of attraction, and hence a huge amount of energy is required to break the crystal lattice. Thus, they possess high melting and boiling points. Because ionic bonds are stronger than covalent bonds, more amount of energy is required to break the ionic bond. Sodium chloride, if you want to melt the sodium chloride, just melt it, not even destroy the bond, just simply melt sodium chloride, you require a temperature of about 800 degrees Celsius. Okay, just to melt it, not even break it. So in ionic compounds, the ions are held tightly together by strong electrostatic force of attraction, and hence a huge amount of energy is required to break the crystal lattice. Thus they possess high melting and boiling points. Next comes stability. These compounds are, solubility. So they are polar in nature. Okay, right? There is a positive center and there is a negative center. Okay, water is also a polar solvent. They will easily be able to dissolve in water. The compounds are soluble in solvents like water, having high polarity and high dielectric constants. Any polar solvent you take, they will easily get dissolved in them. It is because of the fact that polar solvents interact with the ions of the crystal, and further, the high dielectric constant of the solvents cut off the forces of attraction between these two ions. Furthermore, the ions may combine with the solvent to liberate energy called hydration enthalpy, which is adequate to overcome the attractive forces between the ions. Okay, so water not only bonds with the positive and the negative cations and anions of an ionic compound, they rip them apart. Okay, see, water molecule has two positive centers, right? Or two centers. There is a positive center and a negative center. The negative center provided by the oxygen and the positive center provided by the hydrogen. So there is a positive and negative center in the ionic bond also. Sodium is positive and chlorine is negative. Now, the oxygen being a negative charge, the oxygen being a negative charge is now attracting the sodium. which has a positive charge, and the hydrogen which has a positive charge is attracting the chlorine that has a negative charge. Okay, so it is not only forming bonds with the ionic compounds, it is ripping apart the ions. Sodium ions are able to travel freely, chlorine ions are able to travel freely, so you are getting free ions. And when you get free ions, what do? You are able to conduct electricity. Okay, you are able to conduct electricity. Am I being clear, Drupad? Is it easier? Okay, so they are able to conduct electricity because water has an ability to rip apart ionic compounds. It's like a shredder. Okay, if you remove the water, if you evaporate all the water from the salt solution, sodium chloride solution, sodium and chlorine will come back. But when water is present, the sodium and the chlorine can travel freely. They can travel freely all over the molecule, all over the water. And when you pass current through this solution, this aqueous solution, they are able to conduct electricity because of this free movement of ions. Understood? This is known as hydration enthalpy. This is what we call hydration enthalpy. Understood? Which is adequate to overcome the attractive forces between the ions. Next, non-polar solvents such as carbon tetrachloride, benzene, etc. have low dielectric constants and are not able to dissolve ionic compounds. Okay, so there is a popular saying called like dissolves like. What does it mean? A polar solvent is able to dissolve a polar molecule. Water, being a polar solvent, is able to dissolve sodium chloride, which is a polar molecule. Okay. Sorry. Similarly, a non-polar molecule like carbon tetrachloride, it is non-polar, will easily be able to dissolve non-polar molecules. Okay. A non-polar solvent will be able to dissolve a non-polar molecule. Electrical conductivity. Ionic compounds are good conductors of electricity, but not in the solid states. You cannot conduct electricity in the solid state because there are no free moving ions. Okay, they can only be able to conduct electricity in the molten state or the aqueous state, because only in these two states they are free to roam around, they are free to move. So in ionic compounds are good conductors of electricity in aqueous solution or in the molten state because of the presence of free ions in the state. However, they do not conduct electricity in their solid state because of the absence of free ions due to the strong electrostatic force of attraction that binds them. So you have to either melt sodium chloride or you have to dissolve sodium chloride for the actual conduction of current. Am I clear? Am I clear, Drupad? Let's move on. Now, ionic reactions. The compounds split into oppositely charged ions when dissolved in water. Thus, the chemical reaction of these compounds are characteristics of their constituent ions and are known as ionic reactions. These reactions are almost instantaneous. See, when a reaction takes place, the rate of the reaction pretty much depends on how well the ions are held together. When sodium chloride is dissolved in water, as soon as it gets dissolved, it splits into sodium and chlorine. It is ready to react. Okay, it is itching to react with something else because it is already separated. Okay, that is the reason why they are what? They are really, really fast. In covalent compounds, we will see in the later classes or in the later chapters, we will see that their reactions are pretty slow because first things first, you have to break the bond. There is no water molecule, there is nothing available for them to break the bond. So basically, they have to first slowly and slowly break the bond, and once the bond gets broken, the next atom will come and take its place. Okay, it could be an addition reaction or it could be a substitution reaction, but the reactions are usually slower in the case of your covalent bonds. In the case of ionic bonds, because they are split into their ions, they are ready to react as soon as their counterparts. Like for example, in the case of acid or a base, as soon as their counterparts are present, they will do the reaction. They'll complete the reaction. They are very fast. Sodium chloride plus silver nitrate. Okay, sodium chloride plus silver nitrate gives you silver chloride, which forms a precipitate. Silver chloride forms a precipitate and it settles at the bottom. And sodium nitrate. Okay, so silver nitrate plus sodium chloride gives us sodium chloride plus sodium uh, silver chloride plus sodium nitrate. Now, because these two were present as in aqueous solution, they were already split into their ions. So as soon as you brought them next to each other, the reaction just instantaneously finished. It's very fast. Next, non-directional character. The ionic bond is non-directional. This is because each ion is surrounded by oppositely charged ions uniformly distributed around them. What does it mean? If I am sodium, I will have a chlorine here, here. So basically, the chlorine, if it tries to pull me here, this chlorine also trying to pull me in this direction. Attractive forces. So I'm not going here or here. Okay. Similarly, there is a sodium in front of me. There is a sodium behind me. So the pull that this chlorine is going to provide this sodium will be the same as this chlorine providing this sodium. Similarly, at the top and bottom. Okay. So all the pull and the push cancel, not the push, but the pull cancels each other out. So sodium and chlorine. So one sodium surrounded by 6 chlorine atoms basically destroy the directionality altogether. That is the reason why ionic compounds are non-directional in nature. Are you able to understand this fact? This chlorine is pulling this sodium here. This chlorine is pulling this sodium here. So since the pull is the same, what is happening? They're cancelling each other out. Opposite forces of equal magnitude cancel each other out, right? Similarly, this chlorine is pulling the sodium here, this chlorine is pulling the sodium here, and this chlorine is pulling this sodium upward, the downward chlorine is pulling the sodium downwards. So all the forces are of equal magnitude, but they are in opposite directions to each other. Therefore, the net force being applied would automatically become zero. Am I right? Okay, so this is what non-directionality is meant. The formula of an ionic compound can easily be written by knowing the valencies. We know the valency of beryllium is 2 plus and chlorine is 1 minus. All you have to do is cross multiply. So you will get barium chloride, right? Barium has a plus 2 valency, chlorine has a minus 1 valency, and this is how we write barium chloride. Okay, so today's class I'm gonna stop it here. Okay, we have discussed a large section of the first portion of this chapter. Okay, and in the next class we'll continue with this, and then we'll try to start the valence shell electron pair repulsion theory. Okay, we'll finish this and we will start with the Vesper theory. Okay, valence shell electron pair repulsion theory. So I hope you really liked this video. Okay, and I hope you had an opportunity to learn and understand something new. Okay, if you like my videos, please do like, share, and subscribe to my channel. And if you have any doubts, you can put them in the comment, and I will see you in the next video. Bye.